Hey, AP Calculus students, Mr. Meunier back again. Hope we're all doing well. Today we're going to start up on Unit 5. Unit 5 deals with analytical applications of derivatives. Similar to Unit 4, it's applications of derivatives, but less story problems and more using the derivative for analyzing function behavior type deals. Today, we're going to start with a couple of important theorems, one being incredibly important called the mean value theorem. We'll get to that in a moment. Before we get there, Rolle's theorem is kind of an offshoot of the mean value theorem. So this is called Rolle's theorem. And if we were together, I would have you all try this out, and I would grab several of your note packets and flash it on the screen to see what's happening here. But we can do this virtually. So this activity says place 2 points anywhere on the coordinate plane below that have the same y values. So again, 2 dots anywhere as long as they have the same y values. And then connect those 2 points with a continuous function. That means there's no breaks in it. And it also has to be differentiable. We discussed differentiability before. It's basically having no sharp turns. You have to be continuous. If you're continuous, you're differentiable as long as you also don't have a sharp turn. No V shapes. So again, no sharp turns. If I connect this with anything, I kind of made a sharp turn on accident there. You end up with something like this. Or like I said, if we did this together, I'd grab others. People might do something like that. Or maybe people would do something like this. Or people would kind of just do that. There's a lot of ways you can connect those 2 points. But the big idea here, no matter how you do it, every single time you connect them, there's going to be a spot where the horizontal tangent, where the tangent line is horizontal, where you have a horizontal tangent line, which again means when you brush up against the curve, tangent line means you brush against the curve, the slope is 0. So I'm drawing those in with black here. And this green line, that whole thing's horizontal tangent, the whole thing. So idea is we must have a horizontal tangent line, which basically means slope is 0 somewhere. That is Rolle's theorem. And the big thing about that, why that's important, is all of these things, as we've worked through Unit 5, you're going to see it's all about maxes and mins. What's your high spot? What's your low spot? All these black lines here represent, like one I'm on now, that's a minimum value. It's a bottom out point. This is a bottom out point. That's a max. That's a peak. There's another peak. And again, the green one's unusual because it's a flat line. It's always going to be a 0. It's constant. Okay. So again, this is Rolle's theorem. And again, for Rolle's theorem to work, 3 things have to be occurring. You have to have 3 things going on. First thing, always in calculus, is we have to be continuous. Must be continuous. Second thing, you must be differentiable. Must be differentiable. If you're differentiable, you're going to be continuous. And the third thing, y values must match. Continuous on the closed interval. Don't get hung up on that. That just means you have a start and a stop, and they're dots. Differentiable on the open interval. The interval, again, just means open means the endpoints don't matter. So again, closed interval means endpoints matter. They have to be there. Open interval means endpoints do not matter. Okay, so continuous on the closed, you have to have those endpoints. Differentiable on the open, again, the endpoints do not matter. Then the y values must match. That's what this means. If those things happen, you have to have this derivative equal to 0, your slope equal to 0. That must occur. So determine if Rolle's theorem applies to f of x equals x to the fourth minus 2x squared on the interval -2, 2. State thoroughly the reasons why or why not the theorem applies. The theorem does apply. Find the values of c guaranteed by the theorem. Confirm your results by graphing the function in the coordinate plane to the right. So this is our closed interval, -2 to 2. Start at -2, stop at +2. Brackets means those endpoints do matter. For Rolle's theorems to apply, you have to be continuous. Well, this problem is continuous. Discontinuities tend to be not continuous, or like fractions and radicals a lot of times. Those are the big deals. Fractions and radicals tend to not be continuous. Differentiable is going to be differentiable. The big differentiable problem was always absolute values. So again, fractions, radicals, absolute values tend to be where our big mistakes come in. Fractions, radicals, and absolute values. So if that does happen, we should be in good shape here. First thing you have to have is the y values have to match. So f of -2 would be plug -2 into the problem. That's -2 to the fourth minus 2 times -2 squared. That's going to give us a 32 minus, no, that's not bad, 32. That's a 16. What am I thinking? It's going to give us a 16 minus an 8, which is 8. F of +2 is 2 to the fourth minus 2 times 2 squared, which is 16 minus 8, which is also 8. So f of -2 equals f of +2. That's good. The derivative then has to equal 0 somewhere. We have to have a derivative equal to 0. So f prime is going to be 4x cubed minus 4x. This derivative has to equal 0. 4x cubed minus 4x equals 0. We can solve this by factoring 4x out to the front, giving us x squared minus 1 equal to 0. X squared minus 1 factors into x plus 1 and x minus 1 equal to 0. And as I see these, we have solutions at x equal to 0, x equals -1, x equals +1. There's actually 3 spots in this interval where our derivative equals 0, where we have horizontal tangents. And if we graph this, we'll see it, because at -2, we already said we have an answer of +8. So 1, there's 0, -1, -2, 1, 2, 3, 4, 5, 6, 7, 8 up top. +2 is going to be way up here at 8. -1, if I plug -1 in the problem, we get -1. If I plug 0 in the problem, we get 0. If I plug +1 in the problem, we get -1. And this is what the curve looks like. And I think when we plot that, you can see how at -1, there's a bottom out point. At 0, there's a peak. And at +1, there's another bottom out point. There's 3 locations where this has a peak or a valley, where it has a horizontal tangent line. And I knew there had to be at least one, because this problem was continuous, it was differentiable, and the y values matched. All right, so that's Rolle's theorem. Now, mean value theorem takes that a step further. It takes away the y values. For the mean value theorem to work, we still have to be continuous on the closed interval, differentiable on the open interval. Then this is true. This pretty much says if you're continuous and you're differentiable, Your derivative has to equal your slope. The derivative will equal the slope somewhere. Derivative equal the slope somewhere. Or the instantaneous rate of change, instantaneous rate of change will equal the average rate of change somewhere. Somewhere. Derivative must equal the slope. Instantaneous rate of change must equal the average rate of change. F prime, the derivative, must equal this difference quotient slope. If you're continuous and differentiable, that has to happen somewhere. And up top here, this is trying to illustrate that. I'm going to lose my space a little bit when I do this. We'll try to show it to you. So this is saying label the points at A. That's XA. So Y is plug it in, F of A. This is B and F of B. That's 1. Label a segment whose length is F of B minus F of A. So that means Y value F of B minus Y value F of A. There's F of B minus F of A. Label a segment whose length is B minus A. So here's B, take away A. Whoops, go away. B minus A. Then the quotient, F of B minus F of A over B minus A. F of B minus F of A over B minus A. That's rise over run, is the slope of the segment joining 2 points, B, F of B, and A, F of A. Draw in that segment. So if we connect these, that's the slope. That's the rise over the run. F prime C gives the, well, it gives the slope of the line tangent to the curve at the point C, F of C. Again, the derivative gives the slope of a tangent line that brushes up against the curve. Then we have a part 6 on the graph above. Locate the C value that is guaranteed by the mean value theorem and draw a line tangent to the curve at x equals C. So what that means is there has to be somewhere between A and B, there has to be a tangent line slope that's identical to this blue slope I drew connecting the 2 points. So maybe it's right in here. If I draw that in, that's close. We can say that is C. So those 2 lines are parallel to each other. They have the same slope. The derivative value, the tangent line, is the same as the slope value, the secant line. Tangent line has to equal the secant line somewhere. We can see that. So those 2 lines are parallel. Thus, the conclusion of the mean value theorem can be restated as follows. There will be 2 parallel lines, one through the points A, F of A, and B, F of B, and the other is tangent to the curve at the point C, F of C. The tangent line has to equal the secant line. That's another way of saying this. Tangent line equals the secant line somewhere. Tangent line equals the secant line somewhere. All right, and that's the mean value theorem. So determine if the mean value theorem applies to the function f of x equals 3 minus 5 over x on the interval 1 to 5. State thoroughly the reasons why not the theorem applies. If the theorem does apply, find the value of C guaranteed by the theorem. Visually, what is the mean value theorem trying to find? Draw it in. So we have this function on this interval. If mean value theorem is going to work, it has to be continuous on that closed interval. This does have a fraction. Fractions tend to give us problems. But this fraction, the denominator can't be 0, and that's going to happen at x equals 0. So yeah, this has a break, a discontinuity at x equal to 0. That's not a big deal though, because our interval is 1 to 5. 0 is not in that interval. So this is continuous on the closed interval 1 to 5. This is also going to be differentiable. If it's continuous, it's typically differentiable unless you have those absolute values. So since it's continuous and differentiable, there has to be a spot where the slope equals the derivative. So the derivative of this thing, f prime, is going to be, well, the derivative of 3 is a 0. 5 over x, we don't really like that. I'm going to write it as negative 5x to the negative first power. Negative 1 comes to the front, makes it a positive 5. Drop that to a negative 2. 5x to the negative 2 means the derivative is 5 over x squared. 5 over x squared. Okay. We need to know what is the slope between these 2 points. So that would be f of 5 minus f of 1 over 5 minus 1. If we plug 5 into the original problem, 5 divided by 5 is a 1. 3 minus 1 is a 2. Subtract. If we plug 1 in, 5 over 1 is 5. 3 minus 5 is a negative 2. So 2 minus negative 2 is going to give us a positive 4 on top. 5 minus 1 on the bottom is a 4, which means the average rate of change is a 1. The slope between those 2 points is 1. So somewhere, this derivative must equal our slope. The 5 over x squared must equal the positive 1. If I multiply the x squared across, we're going to get 5 equal to x squared. If I take the square root, that's plus or minus radical 5 equals x. I don't want both of those because our interval is 1 to 5. I don't want the negative value. So radical 5 is where this occurs. So the value of C guaranteed by the mean value theorem, MVT, is radical 5. And one more time, what that means is the slope between these two. So at 5, our value is 2. At 1, our value is negative 2. If I connect those two, that's the slope between those 2 points. Slope of 1, rise 1, run 1, rise 1, run 1, rise 1, run 1. But at radical 5, which is a little bit bigger than 2, somewhere in here, the tangent line brushing up against this curve also has a slope of 1. It's identical. Derivative must equal the slope somewhere. Average rate of change must equal the instant rate of change. The tangent line must equal the secant line, somewhere in that gap. And that's what the mean value theorem says, as long as you're continuous on the closed and differentiable on the open. All right, let's skip to example 4. Why does the mean value theorem not apply? Well, for part A here, we have an interval of 2 to 5. This is not a fraction or a radical or anything unusual. It's continuous, but this has a sharp turn at x equals 3. So it's not differentiable on the open interval 2, 5. Again, we have negative 3 to 1, but the fraction here, not continuous. Discontinuity at x equals negative 2. So not continuous on the closed interval, negative 3, 1. And finally, this x to the 2/3, these cubed roots turn vertical at 0 here. That's a vertical. Remember, you can't go vertical. You can't have a sharp turn, you can't go vertical. This tends to happen for the cubed roots. So not differentiable at x equal to 0. All right, got to be continuous, you got to be differentiable. And last, speed trap. 2 stationary police cars equipped with radar 5 miles apart. So again, these cars are 5 miles apart on a highway, as seen in the figure. As a semi-truck passes the first patrol car, it is clocked at 55 miles per hour. Truck is not speeding. 4 minutes later, though, when the truck passes the second patrol car, it's clocked at 50 miles per hour. So he still appears to not be speeding. Prove that the truck did or did not exceed the 55 mile per hour speed limit at some time between the 2 police cars. So again, his instantaneous rate of change, his velocity is the derivative he's going. Somewhere that needs to equal his average rate of change. So I know his average rate of change is going to be his distance divided by his time, his miles divided by his hour, miles traveled divided by time needed. Well, he went 5 miles in 4 minutes. Now, 4 minutes in hour term would be 4/60ths of an hour, which is 1/15th of an hour. We want to have these time needed in hours. He went 5 miles in 1/15th of an hour. 5 divided by 1/15th is 75 miles per hour. He averaged 75 miles per hour. Mean value theorem again says if you have an average, if you have a slope, you have to equal that somewhere. So there was some point in that time frame that he was going 75 miles per hour. So he was definitely speeding. So this is continuous. Say the road's continuous, it's differentiable, there's no sharp turns in the road. Continuous and differentiable. Thus, by mean value theorem, the trucker was going 75 miles per hour at some point and was speeding. They do have speed traps set up like this. I've saw them in California where they just have cameras set up at different intervals taking pictures of your license plates with timestamps and then calculating how long it took you to get between those two. So this is a thing. Well, hope you guys are doing well. Hang in there. Reach out if you got any questions or concerns. Later.